Hi, in this lecture, we will start talking about equations that are more relevant to the fluid dynamics problems. And specifically, we're going to start with advection-diffusion equation. And we're going to talk about the challenges that arise once we go to these types of convective transport problems that are everywhere in fluid mechanics. So first, we're going to start with 1D, and then we'll move to multi-dimensions in next lectures. So in 1D, it turns out that the finite element method and finite difference methods are quite similar and identical. So in what's going to follow in this lecture, we're going to be presenting things in the finite difference setting that's perhaps more familiar, but but keep in mind that this is identical to how the finite element method will also proceed in one dimension. So if you consider the advection-diffusion equation, so this is we have C, which is what we're trying to solve for. C could be concentration or temperature, a scalar field that is advected by velocity. So this is the advection term. The velocity moves around concentration, and then you have an isotropic diffusion term, where according to some diffusivity that determines that's your diffusion coefficient, you can your concentration of your species that you're solving or temperature, it can diffuse out. So then you have this unsteady advection diffusion equation. The important non-dimensional group that dictates the physics of this convection, diffusion, transfer problems is the Pecla number, which is simply a velocity scale V times the length scale L divided by your diffusion coefficient, and it represents the ratio of advection to diffusion. So in most fluid flow problems, the Pecla number is quite large in many transport problems, and because of that, as you will see, the problem becomes numerically difficult to solve. So in general, the larger the Pecla number is, the more difficult it is to solve this advection diffusion equation. Similar to Reynolds number, as it gets larger, it becomes more difficult to solve Navier-Stokes equation. So we're going to be talking about the one-dimensional version of this equation in this lecture. So if I write this equation in 1D, I have partial U partial T plus alpha. So alpha in this lecture will represent my velocity. The higher the alpha, the higher the Pecla number. Alpha times partial U partial X, this is my advection, equals epsilon. Epsilon denotes the diffusion coefficient times the second derivative of U. So we're going to focus on steady problem to make the presentation simpler. So if we ignore the time derivative, we are left with this equation, and we can prescribe boundary conditions. So here I'm prescribing Dirichlet boundary conditions on both ends, and this equation is actually pretty easy to solve analytically. So if you just let partial X, call it V, then you can see that this equation simplifies and you can solve pretty easily for V, and then you integrate and you get the solution U. So this is the analytical solution we find, which is written in terms of the Pecla number, which is alpha, the velocity, times L, the length scale, divided by epsilon, the diffusivity. So this becomes our analytical solution, and U bar is the solution on the right side. So we're assuming the Dirichlet boundary condition is 0 on the left boundary, X equals 0, and at X equals L, it's U bar. So this is my analytical solution. So I would like my numerical solution to provide a good approximation for this. So I can think of this, the physics of this problem, I can divide it into two regimes. The case when diffusion dominates, so this is when Pecla is very small. So in these cases, diffusion dominates, and if that's the case, I can simplify this equation exponential, the e to the power Pecla, since Pecla is pretty small, I can use the Taylor series expansions for the exponential, write it as such. Same thing for the other term. If Pecla is small, so is Pecla X over L. So then I can write it again as a Taylor series expansion. So if you plug these two in here, the ones will cancel out. And what you get is this simple analytical solution. So you can see that in this case, the analytical solution is a linear function, x over L times u bar. So if I plot this, it looks exactly like this. Take the boundary conditions at the two ends and you linearly connect them. And this is kind of, it's expected because if diffusion dominates, if we can basically ignore convection, then we can think of this as a diffusion problem, and we know that the solution to diffusion problems, are linear. You get linear solutions when you have just pure diffusion. So this is the linear solution that we get. Now, it turns out in most fluid flow problems, the Peclet number is quite large. And you have advection-dominated flows. This even happens in microscale flows because a lot of times, even in microscale flows where you have a small length scale L, for many chemicals, for example, if you're doing mass transport, the diffusion coefficient epsilon is quite small for the diffusivity in liquids like water. So, for the case of mass transport problems of many chemicals, you even at the small scales, you still can get pretty large Peclet numbers. So this is a regime where advection dominates. So if you look at the analytical equation, if Peclet is large, these exponential terms are very large. So basically, I can ignore the one next to them. So this is what I get. If I simplify, it becomes something like this. Exponential of Peclet times x over L minus 1. Now, x over L is between 0 to 1. So when you do minus 1, this whole term is negative. So you have exponential of a negative number times Peclet, and Peclet is very large. So you have exponential of a large negative number. So this becomes pretty much 0, right? The only part that this cannot be assumed to be 0 when x over L is close to 1. Because when x over L is close to 1, you get 0 here. So you have exponential of 0, which is 1. So that's just 1 times u bar. So if you plot this, this is what you get. Your solution is pretty much 0 everywhere, right? And then suddenly in a very thin boundary layer that scales with Peclet, you're suddenly jumping to the u bar value. So this is your thin boundary. And this is what this analytical equation tells you. So this is the type of solution that you get in this case, which is the numerically challenging case to solve. And I have to remind you that we've assumed the velocity alpha to be positive. So this is a problem where we have convective transport from left to right. Okay, now let's do the finite difference approximation for this advection-diffusion equation. So if I do the discretization of my 1D domain into these elements, if I consider 3 nodes, node I, and then I plus 1, the node to the right, I minus 1, the upstream node, the flow goes from left to right, and then the size, the delta x, I'm going to denote with h. So if I consider this, if I do the discretization of my PDE, if I want to do second order difference, this is how it looks. So partial u partial x, this is the discretization at node I for partial u partial x. So this is my term that I'm discretizing with finite difference times alpha. So this is second order discretization for first derivative. And then my second spatial derivative, this is again the finite difference discretization for that. So I have the diffusion coefficient here too. And h is my mesh h size. So now if you look at this finite difference discretization, I have 3 unknowns here. So I can group the equation as such, factor everything that has ui plus 1, ui minus 1. So I have 3 coefficients here if I group things accordingly. I have a, which is given by minus velocity divided by 2 plus diffusivity over h. And since I assumed alpha to be positive, the flow to be from left to right, the diffusion coefficient is always positive. H is, of course, positive. So this term A is always negative. Similarly, B only has diffusivity and H. So this is also always positive. But then the C term, this term C that gets multiplied by ui minus 1, this one is not clear if it's positive or negative. So it could be either positive or negative. And we're going to come back to this. So now if I group everything, so assuming I have n nodes, right? So if I, calculate all of these ABCs, I group all my equations, so everything comes down to solving these linear systems of equation, where this vector of u's are my unknowns. I have my right-hand side, in this case, zeros, and then my left-hand side matrix is a tridiagonal matrix. And of course, on the right-hand side, I would also need to modify it to make sure my Dirichlet boundary conditions are satisfied. Okay, now the matrix is a tridiagonal matrix, so it's simple to work with. It's a sparse matrix. Everywhere else is zero. You have the three diagonal entries that are non-zero because of the specific form of this finite difference scheme. So now, if I look into how the equation behaves, let me first assume that C is negative. So C was the part that I didn't know if it was positive or negative. It really depends on how alpha, epsilon, and h, my velocity, my diffusion coefficient, my mesh edge size, how they compare with respect to each other. So if I assume that C is negative, so this term is negative, then it means that alpha times h over 2 epsilon is negative. And I'm going to actually give this a name. If you look at this term, it looks pretty similar to our Peclet number, right? You have velocity times length scale. In this case, the length scale is the mesh edge size h divided by diffusion coefficient, and then there's a factor 2, which is all right. So then I can, I'm going to call this the grid Peclet number, right? So essentially, the grid Peclet number is the same as the Peclet number, but the difference being that instead of the length scale of the geometry, the entire domain, I'm using the mesh edge size. And in this case, I also have this factor 2 here. Okay, so the first condition implies that the grid Peclet number is less than 1. Now, if that is the case, if I go back to my linear system of equations, if I consider the first equation I get, which is b times u1 plus c times u2 equals 0, this equation, I argue that b is always positive, c I assume to be negative. So if you look at this equation, what it means is that u1 and u2 are the same sign, because you can take u2 to the other side. C is negative, b is positive. There's a negative here, so this whole thing is positive. So the sign of u1 and u2 will be the same. Remember, u1 and u2 are my leftmost, so here, 1 and 2 are my two nodes that are next to each other on the left side of the mesh, or the upstream portion where the flow is coming from. And I can write the next equation that I get from this linear system of equations. As you can see here, if you plug the first one to the second one, and you look at the terms given the signs that C is always, we assume C to be negative, and this term you can easily convince yourself that's always positive. So then you will see that again, U2 and U3 have the same sign. So what this means is that in this case, where C is negative, meaning that the grid Peclet number is less than 1, as I move through my mesh, my nodal solutions, U1, U2, U3, so on, they do not change sign. So I have, or in other words, I have no oscillatory solution. My solution monotonically increases from 0 to L in a nice way. And this is what I like to have, right? A big challenge with solving convection-dominated problems, which happen a lot in fluid mechanics, is that you get these spurious numerical oscillations that are not desirable because they're not part of the physics. They're not real. They're numerical. And they can also cause stability problems. So now, well, in this case, where grid Peclet is less than 1, I proved that I do not get any of these oscillations. My solution behaves nicely. Now, what if C is positive, meaning that the grid Peclet number is greater than 1? In that case, if I go back and do the same analysis, what I'm going to see is that, so now C is positive, I'm going to see that U1 and U2 have opposite signs. And I can confirm that this happens throughout. So as I move from left to right on my mesh, I get these oscillatory solutions. And this oscillatory solution is not good. This is not physical. I want us to have a solution that behaves monotonically in a nice, smooth way, but I'm getting these spurious oscillations, which we also know as numerical wiggles. So now the question is, how do I eliminate these numerical wiggles? Okay, because they're not desirable. I don't want to have them in my CFD solution. Well, from this analysis, you already have the first solution. The first solution is that, okay, choose your grid Peclet number to be less than 1, right? And then this issue goes away. Now, if you look at the grid Peclet number, alpha, the diffusion coefficient, or rather the velocity, and epsilon, the diffusion coefficient, these two you don't control. This is what you're given. These are the known parameters of the problem. The only parameter you can control in your grid Peclet number is the mesh edge size h. So what it means is that if you want to solve this problem, your first choice is to make a very fine mesh, so h being very, very small, such that you can ensure that your grid Peclet number is less than 1. Okay, so if you can do that, then the problem will be solved. Now, the problem is that in most problems, especially when you're dealing with more and more convection-dominated problems, it will be very, very difficult to choose a mesh that satisfies this, meaning that your mesh will be very, very tiny elements. So it will be computationally very, very expensive, and most of the time not even feasible to solve the problem if you require the grid Peclet number to be always less than 1. So this can be, very difficult to solve, especially if you move away from the 1D problem and go to multi-dimensions. Okay, so that's the first choice. Always making a finer mesh, helps, and so does it in this case. So, but it's a lot of times it's not practical. Now, the second more common solution is to use what's known as upwinding. So, it's known as upwinding in the finite difference community. In the finite element community, we know it as stabilizations, and we're going to talk more about it in this course. So now, the idea is that for the advection terms, for alpha partial u partial x, instead of using the central difference, which is second order accurate, I'm going to use a first order approximation that looks like this. Okay, so alpha ui minus 1 over h. So I'm going to plug this into my finite difference or finite element discretization. Okay, and I'm going to leave the second derivative the same second order approximation that it was. Now, the reason I did ui minus I minus 1 is because I assumed alpha to be positive. And when alpha is positive, if you come back here, the information, the flow propagates from left to right. Think of this as a parabolic PDE. The flow is going from left to right. So the information goes from left to right. So when I'm doing my spatial discretization around I, and I want to do a one-sided discretization, I want to do an upwinding, a first order discretization, I'm going to use the node that is to my left. I'm going to use I minus 1. I'm not going to use I plus 1 because I know the information comes from the left side. The flow is positive, alpha is positive, the velocity is positive from left to right. So in my discretization I use, go down here, I use ui minus 1 over h. Now, if alpha was negative, if your velocity was from right to the left, then you would use what's known as downwinding instead of upwinding. So here you would have ui plus 1 minus ui because information propagates from the node after ui to ui because the flow is from right to left. And if you have a multi-directional flow, the practice is that you can switch between upwinding and downwinding based on the streamline direction. Okay, so now if I do this, what happens is that the first thing that happens is that I lose my order of accuracy. Because even if in one term, even though I'm still using second order accurate for my diffusion term, it doesn't matter because I've dropped the order of accuracy in my first derivative. So the entire accuracy is going to drop to first order. I'm going to be first order accurate. And I actually can see what's the extra price here that I'm paying. If I look at the first order convection term, that now I have this first order advection term, if I do Taylor series expansion, okay, if I do Taylor series, if I write ui minus 1 in terms of ui plus Taylor series expansion, this is what I get. So this is approximating alpha velocity times partial x at node I, which is exactly what I wanted to approximate, right? And I took this term and replaced it with this finite difference counterpart here. However, now I also have this extra term. And if you look at this extra term, it's alpha, your velocity, times h, your mesh h size, divided by 2, times the second derivative of the solution. Now, this second derivative is like a diffusion. So and this is minus. So this is, so if you take this term to the right-hand side where the diffusion actually sits, you're going to see that what you really have is that really what you're doing by doing this stabilization or upwinding, what you're doing is that you're replacing your diffusion coefficient epsilon by a new diffusion coefficient, that's epsilon, plus this coefficient taken to the right-hand side, so positive, alpha times h over 2. So this alpha h over 2 is what I call artificial diffusion. It's what's getting added to your physical diffusion, okay? So you have this artificial diffusion. And this artificial diffusion, is what does the job of stabilization, okay? This is what is helping you stabilize the solution. Now, artificial diffusion may sound a little bit not accurate, I guess, but I mean, it does have some nice properties. The first property is that if you look at this artificial diffusion, it's proportional to h being your mesh h size. So what it means is that if I'm using a stabilized method or this upwinding scheme to solve this 1D advection-diffusion equation, I will not get wiggles, of course. That's good. I'm going to get rid of those spurious oscillations. But if I'm worried about dissipating my solution too much and reducing accuracy, I can kind of convince myself by taking my mesh h size, and making it finer and finer. Because as you can see here, as I make my mesh finer, the artificial diffusion becomes smaller and smaller. So not only your accuracy, your finite difference accuracy becomes, of course, more accurate the finer your mesh is, but also on top of that, the artificial diffusion effect becomes smaller and smaller as your mesh h size becomes smaller. So this is consistent. This is what we like. Even though we've introduced stabilization, we've introduced artificial diffusion, we like it to be such that as we make our mesh finer and finer, as we do those mesh-independent studies, we want its effect to become smaller and smaller. And this is exactly what we see here. So that is good. Now, another thing you see that's also good is that this artificial diffusion scales with alpha. Remember, alpha was your velocity. So, for example, if you take a problem and let's say your velocity is varying, for example, right? And you're varying the velocity, or the velocity is time dependent or whatever. As your velocity becomes smaller and smaller, you know that you don't probably need artificial diffusion as much anymore because your velocity is becoming smaller, your Peck is becoming smaller, you're becoming more diffusion is starting to play a bigger role. Advection is becoming less important. And this artificial diffusion term automatically kind of conforms with that with physics, right? Because if you look at it, as alpha becomes smaller, the effect of this parameter also becomes small. So that is also good. And another nice thing about this artificial diffusion coefficient is that in practice, sometimes people multiply this whole term by some beta, for example, some free parameter beta. So you can take this artificial diffusion coefficient, multiply it by a free parameter beta, and okay, in that case, you would essentially, don't use basically this. Do you use your regular second order accurate scheme, right? You'll just use your second order accurate scheme, and you'll just add this to your diffusion coefficient, right? That's alternative approach, right? So in that case, you can essentially just multiply this artificial diffusion by any coefficient you want and make that coefficient be a free parameter. And it turns out that for 1D problems, you can prove that by doing that, you can select that free parameter beta that multiplies your artificial diffusion such that your nodal solutions to the 1D advection diffusion coefficient are nodally exact. So that you can prove. If you're interested in that, you can check out chapter 6 in the book by Kuzmin, Dmitry Kuzmin book, the Cyan book. That's the second book that was introduced in the first lecture. And you can see that how you can prove actually that with an appropriate choice of that free parameter, which turns out to be as a function of a grid Peclet number, then you can make this numerical discretization to be exact. Even though you're having artificial diffusion, you're scaling it in a smart way such that your solution is exact. So you're getting exact and correct solutions. And this is you can only show these things for one-dimensional cases. And that kind of motivates us for whole finite element stabilization literature, is that a lot of times when we introduce stabilization parameters, they include some free parameter. So in this case, this artificial diffusion multiplied by some free parameter beta. And those free parameters, often we can study them in a simplified one-dimensional equation where we know things very well. We can derive things very easily, find what they are. And those free parameters often are grid dependent. So they're usually, for example, functions of the grid Peclet number. Or if you have a time-dependent problem, maybe they're a function of time step. So you find those form, or you hypothesize, you do your numerical tests in 1D, you tune them to get exact values for them, and then you use those stabilization parameters in the more challenging multidimensional case. Okay, so we will be talking more about this in next lectures.